right, so if you want to look at and go all the way back to the very beginning of your packet, let's talk about what we're doing today. We have our quiz today, and for the most part, it's on sections 1 and 2. We want to make sure that you're good with that arc length, sector area, that part of the whole conversation. There will be some tangent conversations where we're going to hold off on some of the chord relationships until our next assessment. We do have a lesson to get to today, so I want to make sure that we can review and quiz and get to our lesson. When we look through what we've talked about vocabulary, we've talked about circumference and figuring out where pi comes from and those relationships, looking at arc length, more vocabulary, practice, sector area, where does area of a circle come from, and practicing again these conversations about a sector and a segment. When you look at all of this practice that you've done as you page through your packet, your number one consideration is this slide. So for everything that you need to know, it's this slide. And a couple kids came in early this morning to practice and talk about this. And here's what we need you to know as a geometry honors student. Any one of these variables is fair game for us to ask you about. We can ask you to solve for central angle or arc measure. We can ask you to solve for arc length. We can ask you to solve for the radius. We can ask you to solve for the diameter. We can ask you to solve for the sector area. Again, radius or the area of the circle. So when you look at this extended ratio that we talked about in Unit 5, all of those part to whole conversations are what you need to be fluent in. And if you are an equation person, you need to understand that even though we write an equation similar to this, where you say that your arc length is equal to your part of your whole, and if you're talking about area, your whole is pi r squared, you need to understand that any one of those variables, fair game. So instead of memorizing something in isolation of how to solve just for arc length or how to solve just for sector area, what we need you to understand is this whole relationship and how you can tease out and solve for using algebra whatever variable you're missing. And that's kind of cool, because having the ability to do your properties, I was talking to a kid this morning about bringing out Keith Berkeley, go ahead and multiply by the reciprocal to free up that variable. Paying attention to those equation solving skills that you got in algebra, subtracting the same thing from each side, multiplying the same thing from each side, dividing each side by the same thing. Those are how you untangle a variable that you're looking for. When we talked about some of our angle and chord relationships, this story is really the biggest one, because these three things all play into one big idea. Number one, if you have a diameter, we talked about we'll make this fit, our perpendicular relationship and our bisected chord. Most of the questions that people brought into me this morning that they got stuck on are understanding how those three things are all related. Anytime you have two, you have the third. If you have a diameter that's perpendicular, you know that chord is bisected. If you have a diameter that bisects a chord, you know they're perpendicular. Anytime you have a perpendicular relationship and a bisected chord, that bisector is a diameter. And the most important part about this is this creates all kind of right angle relationships. So now we've got Pythagoras, we've got our special right triangles, everything from unit 6, fair game. Trig, special right triangles, altitude to the hypotenuse, all of it, fair game. All right, we went ahead and talked about tangent lines. And the biggest thing about here is if a line is tangent to a circle, that radius that's drawn to that point of tangency, guess what it's going to create? A right angle. They're perpendicular. And because they're perpendicular, what do you now have to be on the lookout for? Right triangles. Right angles, right triangles, Pythagoras, trig, special right triangles. This conversation here, when you have an exterior point and two tangents going out to that point, those line segments are going to be congruent. And we talked about why they're congruent. Because I have these radii that are congruent, and I know that they intersect those tangents at right angles, I know I have hypotenuse leg congruence, so through CPCTC, those tangent segments are congruent. So we can have all of that math all rolled in to one big conversation. All right, I asked you to finish these practice, so we want to make sure you have your answers. When you look at Circle C, well, everybody check in and make sure that you're with me on this right page. For Circle C, with a given radius of 6, find the value of x. What's tricky about this problem? There's two tricky things. What do you think, God?
Should I tell you the radius and like not the full diameter so you can get tripped up on the triangle?
Absolutely. Absolutely. It tells you the radius. And you need to know that you double that radius for that diameter for the side of the triangle. Everybody stare at it. See the radius? See it doubled? All right, what else is tricky about that problem? What else do you need to know? You're looking at this problem on an SOL, you're like, I can't solve that. What else do you need to know from this very unit that you just learned? Brand new concept. What's the relationship between the radius and the point of tangency on that tangent? What are they? Say it out loud. Everybody, what is it? They're perpendicular. So here's what you need to know. You need to know they're perpendicular, and because they're perpendicular, what's the angle? 90 degrees. Because it's a right angle, what can you use? Pythagoras. We talked about him on day 1, and we're still talking about him. A squared plus b squared is c squared. You need to be ready to solve for any one of those triangle sides. Whether I ask you to solve for the short leg, the long leg, or the hypotenuse, whether it's an isosceles triangle and you're using your 45, 45, 90, whether you don't have enough information but an angle and you need to pull out your trig, any side, any angle of that triangle, fair game. So just because we do it this way once doesn't mean it's going to be that way always. So you need to kind of expand your mind a little bit and think, okay, what other kind of questions could they ask me about this same concept? That's how our thinkers do better on quizzes and tests. If you're a thinker, you look at a sample problem and you ask yourself, how else could this question be asked? What else could they do to change this? You should be thinking about an A and B version of a quiz. What do you think she might change to make my question different from the person sitting next to me? Are you going to change which leg I'm solving for? Are you going to change the measure of my diameter? Are you going to give me the diameter instead of the radius? So anything that I can change about that problem is what opens up different possibilities. And you need to be ready for it all. Does that make sense? Our thinkers are our successful math students for sure. All right, number 2, what do I do with those tangent segments? What do I do?
Since they're congruent, you can put them equal to each other.
Set them equal to each other. So there's no need for you to draw the radius. There's no need for you to draw a triangle. There's no need for you to do anything other than know that you're allowed to set these two equal to each other, and then we're back to algebra. So why do I have a box around plus or minus? What's up with that? Whenever you take the square root of a number to solve for x, there's two possibilities for that answer. Because if I'm asking for two numbers that multiply together to give me 25, I can either do 5 times 5 or negative 5 times negative 5. Both give me positive 25. So there's two possible answers. In geometry, frequently, we don't even bother with the negative because distance can't be negative and we don't worry about it. But if I plug negative 5 into this answer, is it a possible solution? So we do this plus or minus, telling you, here, there's two answers that are going to make that true. Positive 5 and negative 5. All right. After this, we talked about, here we are standing 4 feet from a fountain. And again, we have to expand our mind to think about the relationships that I'm looking at. This radius and this tangent line are perpendicular, which means I've got myself a right angle, which means I've got myself a right triangle, which means I can bring Pythagoras in. Once I tap Pythagoras, I'm like, all right, short leg, long leg, hypotenuse. Take a look at how tricky this is. I'm standing 4 feet from the fountain. Do you see how that fountain's radius is always the same? That is the number one trick they do for circles. Every single distance from the center to the outside of the circle is the same, no matter what radius you draw. So this radius is going to have the same measure as that radius. So when I go to write it, short leg squared plus long leg squared is going to be equal to my radius squared. That's some polynomial work for you to do. Remember FOIL, first, outer, inner, last. That's your double distributed property. R plus 4 squared. R squared plus 8 squared plus 16. Once I get that written out, do you see how my R squareds cancel out? I've got the same thing on both sides of the equation. Do you see it? And then I end up with a simple linear equation, no problem. How'd you do with that one? Tricky, for sure. All right, this, and then we moved into our chord and arc theorems. And with our chord and arc theorems, remember I told you when I taught Caroline? Duh. She's like, these are the duh theorems. I'm like, I'm with you. Because if your angles are the same, your arc measures are the same, if your radii, if it's in the same circle or congruent circles, and that's what this sentence means with each one. Within a circle or in congruent circles, if I have the same radius, then congruent central angles and congruent arc measures are going to lead to congruent arc lengths. Congruent arc lengths are going to give me congruent chords. So the shortest distance possible between those two. A and B are those values that define both the angle and the arc. And they create line segments. We call that the intercepted arc. So they're all going to be congruent. And this page says it 4 different ways. 2 minor arcs are congruent if and only if their corresponding chords are congruent. So we go from angles to arcs to chords. So in this conversation, because in circle X and E, because circle X and E are congruent, like everything is congruent. Because the circles are congruent, the radii are congruent, because the radii are congruent, the angles are congruent, the arcs are congruent, the chords are congruent, no worries. In the same circle or in congruent circles, 2 chords are congruent if and only if they're equidistant from the center. So here are two chords, and they're special kind of chords that go through the center. What do I call them? What's a special kind of chord that goes through the center? Everybody say it out loud. Everybody out loud. What are they? They're diameters. That is the widest part of the circle. I want you to picture me at the center of the circle, pushing both of the diameters out in opposite directions. If I push this one up and I push this one down, if I push them the same level, they're going to be the same distance away from the center, which means they're going to be cut off on each side and therefore congruent. So any two chords that are the same distance from the center of the circle, they're going to be congruent. And I think all the times about pushing a diameter out, and if they're pushed out the same way, then those chords are going to be shrunk the same amount. And here's our favorite diameter perpendicular bisector conversation. Did anybody Google the Veil skier and read the story? Very sad. If he had had an avalanche beacon, they would have found him by using this very geometry. Finding the signal, walking across, coming halfway, therefore it's bisected. Walking at a right angle, therefore it's the diameter. Finding this halfway of the diameter, therefore the center of the circle, the source of the signal, they would have found that skier. He'd be alive today because they know how to use that geometry. All right, just so you have some answers here, find the measure of each arc. Measure is always in degrees. Number 5, in circle X, AC is a diameter. The distance from E to D is the same as the distance from E to B. What can you conclude? So let's talk about this a little bit. I know the triangle is isosceles because of EB and ED being congruent. Therefore, I know that these angles are congruent because of the isosceles base angle theorem. And then I'm also going to know that this is a right angle and that these are bisected because of the perpendicular bisector theorem. So because these are bisected, these are congruent, the angles are fine, I have congruent right triangles. And if this is bisected and these have the same length, then this chord is also going to be bisected. So we'll talk about that as what you can conclude from that conversation. Find the measure of KLM. Same conversation. Here's our diameter. Here's our bisected chord. So I can set those two arcs equal to each other. For these three, you're finding the value of x, and it says to the nearest tenth. And every single one of these is working with that bisected diameter chord conversation. So for this one, understanding that this segment here is a diameter, therefore it's bisected a right angle, and I can go ahead and solve. That makes this segment 7. So I can use Pythagoras to solve for that short leg. In this middle one, you're solving for x, but first I'm going to solve for this side here. And then once I double it, I can get x. Because I can just use Pythagoras here to solve for this leg here, knowing that that's going to be bisected, I can double it. Here, and my diagram is a little muddied compared to yours, but you can draw a radius wherever you want. So So when you draw that radius, it's gonna have the same measure, so I know I'm solving for the x that's over on the other side of the circle, but I can go ahead and make some triangles. So make sure you know you're allowed to make some triangles and draw a radius wherever you want. Go ahead.
So for the first one, and all of these, are you just allowed to extend the line?
Absolutely. If it's something that connects, then you know you have a diameter, because the diameter is a chord that goes through the center of the circle. Absolutely.
Okay.
Any questions on these? Okay. We asked you to do the quiz review and the Delta Math, and I'm confident that you are all at different stages of done this. So the key was posted on Schoology. You need to know this vocabulary, and you need to know how to find arc length, circumference, radius. You need to know how to find sector area. So I hope you checked your work there. Lots of questions about the tractor tire and the mountain bike. Basically what you're looking at is a revolution of a tire is the circumference. That's the distance around. So if I roll a tire once, if I take this round cylinder and I roll it, one revolution is the distance of the circumference. So if I have a big tire, that's a tractor trailer, it's 36 inches in diameter. If I have a mountain bike that's 28 inches in diameter, in order to go the same distance, that little tire has to revolve a lot more. If you've ever seen an adult on a bike ride with their kid, either you go on a bike path or you're around your block in the neighborhood, next time you're watching an adult ride a bike next to a kid riding a bike, watch their feet and their tires, because on the little kiddie tires, that little kid is pedaling to get his tires to rotate to go around. And the adult is doing this much slower, because in order for the bike to move the same revolution, the kid has to pedal a whole lot more than the adult. So next time you see a parent and a kid on the bike, look at the tires, look at the revolution, and look at that kid pedaling. That kid's working a lot harder. Anytime you're finding area, you can go ahead and subtract their values. So find the area of a square, taking out the circle. Once you enter into the conversation of pi, you're not going to be able to keep your values rational. This part here about tangents, making sure you know that the radius is perpendicular to the point of tangency, the congruent segments, and then solving problems like this. Now here we brought in some Pythagorean converse by asking you, once you solve for it, is it acute right or obtuse, depending on that value. And again, our perpendicular bisecting diameter of a chord gives us those values. If you were not able to finish these when you finish your quiz, because your quiz doesn't go as deep into the chords, it stops at the tangents, I want you to go ahead back and finish your work and then check it on Schoology, including the two proofs, proving those triangles are congruent, and then proving these two triangles are congruent. So those two conversations are on Schoology. All right, back to our warm-up. Here you had a warm-up. Would you please turn to your partner and treat it like it were the quiz. Look at your partner and say, let's go. All right, for your major and minor arc, maybe you picked a different one than me. That's fine. My minor arc, I picked X to Z. You could have picked Z to W. You could have reversed the letters. You're just looking for any arc that has a measure that's less than 180 degrees. For my major arc, I went the other way around the circle from X to Z, so I included W, and that's why W is there. You need to let somebody know you're going the other way around the circle. Your semicircle is going to be half of the circle. So if you're talking about X, W, if you care which direction you're going, include a Z or another letter. Otherwise, from X to W, anytime that you are using the diameter endpoints, you're getting a semicircle. Measure of arc XZ. I'm going to go ahead and say that 2A plus 24 plus this A has to equal to 180. I get A has a value of 52, so this has a 52 degree measure, meaning this one's going to be supplementary and giving me a 128 degree measure. If I need to find the length, it's a conversation including a part of a circumference and its regular linear units. If I'm looking for an area, it's the fraction of the area and my units are squared. If you're asked to give an answer in terms of pi, then your answer is a fraction, a rational number including pi. If you're asked to round to the nearest hundredths. Coulter, what's on your mind?
You said 128 over 360 for the area, but that would be if you used XZW.
Oh, did I do the wrong one?
Yeah, it should be 52 over.
Good catch. Go put a Smarty up. Let's fix that. So he's telling me wrong here. So that's going to change. I was just using the same value and not reading fast enough. Nice catch, Coulter. All right, so then this instead is going to be a 52, right? And when I do 52 divided by 360, that fraction times 25, because that's my r squared, that gives me that, and then math, frac, enter, 65/18. Does that sound right? All right. So we end up with 65/18 pi, and that times pi is going to give me 11.34, and that's units squared. Is that better? Uh-oh, what did I do?
Are you looking, like on the quiz, is it gonna say when you're looking for units of pi and when you're looking for like, close?
Yeah, so pay attention to how they ask you to do your answers. Delta math sometimes rounds to the nearest tenth or hundredth. You gotta read to know. If they ask you to give your answer in terms of pi, that means they want a pi in your answer and they want a rational value or the exact value. The other wording is that is if they ask you for exact. If somebody asks you for exact, then you're keeping pi, you're not breaking it.
So to be safe, if I wrote both, they would be correct.
Absolutely. All right. So a little review: tangents and chords, perpendicular, congruent, and then the back of this is directly from your homework. We've already solved both of these, no problem. When you finish the quiz, when we were in Stinger yesterday, that blue piece of paper that you picked up that we talked about, anybody have any questions from what we talked about with the JLabs? I'm not making that up, right? We talked yesterday? Okay, so if you missed our Stinger yesterday, you want to make sure you pick up that blue piece of paper. And if you have time to do, while you're waiting for everybody else to finish the quiz, you're welcome to start, but remember, if you start one and then not finish it, your work is gone. So don't do more than 5 or 10 while you're waiting for others to finish up their quizzes too. Does that make sense? Right, clear desks. I want to follow up on the conversation with this blue piece of paper. We want to make sure that you understand about the emailing me your results. If you don't get at least a 70% on the quiz, don't send it to me because I'm not going to count it. I want to make sure you know that whatever quiz you send me, when they all go into, I've set up a thing in my email where once it comes from JLab, it goes into a separate box. When I check it, it sorts by your name. So I can sort it that way to see, because they're all from the JLab administrator, but your name is in the subject, so it puts them all together, and it makes it easy for me to see all the quizzes you send me at the same time. That being said, don't send me duplicates, because I see that they're duplicates. So if I feel like you're trying to get more credit for quizzes that you didn't take, we'll just go ahead and call it a 0. So make sure that, and if you send me a duplicate by accident, just let me know, like, hey, I think I sent you this twice, sorry about that. But we want to make sure that you reach those 100 questions with integrity, for sure. When you're emailing me, make sure it's TJ Glazier on that blue sheet. You want to make sure you write, because with my email underlined, sometimes that J looks like an I, and kids get that mixed up. So make sure you're sending it to tjglazier@fcps.edu, and I'll be sure to get them. On the back of this paper, we talked yesterday about our final exam schedule and when your final exam is, what topics it's going to cover. We're going to pull from these 3 sections, and the grades from each of these 3 sections will be averaged with what's already in your SIS grade book. So 5% of Standard 6, 4% of Standard 7, and 5% of Standard 8 are up for grabs. So we talked again about whether or not you want to retake for Unit 7. If you want to retake, you are allowed to retake. We're not telling you no. But in this season of high stakes testing and a lot going on, you have better things to do with your time than to come and take a test again. So what we're trying to do is give you opportunities to improve your grade and make the most efficient use of your time. So doing corrections on Unit 7, we're offering half points back. So we want to make sure you understand that. But it's not guaranteed. If they're not quality, good corrections, you're not getting those points for free. So make sure you're doing a quality job on your ICTOPs. And you'll see Unit 7 again on the final. That'll give you a chance to average that grade and bring it up. Any questions about the final or how we're treating your grades? If you find yourself curious in the future, please don't hesitate to ask. All right. Today we're going to talk about 8.4, super quick. And here's a question for you. If I'm at a movie theater and the movie screen, I want you to picture that being the diameter of a circle around that arc. Which is the best seat? A, B, C, D, or E? Turn to your partner and talk about it. Go. I heard lots of C's. I didn't even get a chance to pause the video. And you're like, C, I'm sitting in C. All right. We're going to come back and revisit this question in a minute. Some new vocabulary for you: inscribed angle, intercepted arc, inscribed polygon, and a circumscribed circle. An inscribed angle is an angle in the interior of a circle whose vertex is on the circle, and it's created by 2 chords that share that same endpoint. So I want you to take a look at our inscribed angles theorem. Do you see here, here's 2 chords, chord AD, chord BD. Notice the vertex of that angle is sitting on the circle. That's an inscribed angle. What's in green is the central angle. We know that. What's in red is an inscribed angle. And I want you to picture clicking on that vertex C that's at the center of the circle and dragging it out. So if I click here and I was able to drag this angle out, are you surprised that the measure of the inscribed angle is half of the central angle? Because when I pull it and I stretch it back, do you see how that angle gets smaller? So it's a 1-to-2 ratio. So my central angle, whatever that measure is, the same as the measure of my intercepted arc. But that inscribed angle is going to be 1/2 of that measure. So my intercepted arc is AB. My central angle, ACB. Pull it out, my inscribed angle is going to be 1/2 that measure. So that's one new thing that we need to keep track of, that they're going to give us lots of practice and whatnot to solve. Here's 3 corollaries that go along with that. And a corollary is, hey, along with that theory, there's some related conversations that are worth talking about in specific. If I have 2 different angles that are created from the same intercepted arc, do you see how this green angle ACB and this orange angle ADB both have arc AB as its intercepted arc? Do you see how they're both created from AB? Do you see how both of them have a vertex that sits right on the circle? They're the same measure. They are 1/2 of that angle measure. 1/2 of the central angle, 1/2 of the intercepted arc. Guess what that means? Every single one of these seats in the movie theater has the same view. They all have the same access. They all have the same angle to the movie screen. So guess what? All those 5 seats are the same. Whether you choose A, B, C, D, or E, you have the same view, the same angle to the movie screen. Kind of crazy when you think about it, right? So whether you pick A, B, or C, or D, you have the same view to the movie screen. All right, here's corollary number 2. If your intercepted arc, pay attention to the vocabulary, your intercepted arc is that arc that defines that inscribed angle. If your intercepted arc is a semicircle, CAC, that's a diameter. This diameter divides this circle in half. This arc is 1/2 of that circle. If that's true, it has a measure of 180 degrees. Got it. Because, and then guess what it makes this angle worth? What's 1/2 of 180?
90.
Oh, hello, right angle. Hello, Pythagoras. Hello. A squared plus B squared is C squared. Hello, right triangles that are special. Hello, trigonometry. Every time we see a right angle, we have to say hello to that implementation of that Unit 6 math that we love. Guess what? My movie screen, that was a diameter. So if my picture were to scale, what would each of these angle measures be? 90 degrees. That's your maximum view. So you have that 90-degree view on that circle. All right, corollary number 3, and this one's kind of cool. If you have a quadrilateral inscribed inside a circle, so if something is inscribed, its vertices are on the circle. So if it's inscribed, do you remember when we were making our angle bisectors that gave us a circle that was inscribed inside the triangle? Inscribed is inside. That quadrilateral is inscribed. It's inside of that circle. Check it out. Do you see how this orange angle is created from this intercepted arc? Do you see how this blue angle is created from this intercepted arc? Do you see how orange plus blue gives you the whole circle? What is the whole circle? What degrees?
360.
360. So that means that those angles added together are 1/2 of 360 or 180. So that means that if you have a quadrilateral inscribed inside of a circle, these two angles are going to be supplementary. Kind of cool when you think about it. All right. Our last angle conversation is if I have a tangent and this chord intersects, so my tangent line here intersects this chord here at that point of tangency, then the angles are going to be equal to 1/2 of the intercepted arc. So you can think about them as inscribed angles where we just opened up that angle all the way as far as we could. So that blue arc X, that distance around, and that angle number 2, 1/2 of each other. Right. All of these make sense to me because I've been teaching them for, I don't know, 17 years. So I remember them. And I look at them and I'm like, oh, I see it. It makes perfect sense. It's all new information to you. And unless you do something with this content, you won't remember it. If you page back through the packet, the quality of your work is directly proportional to the quality of your learning. If you've been doing the homework, if you've been thinking about the content, if you've been processing it, if you've been working, if you've been doing the Delta math, then you're feeling pretty good about this. But the circles unit is tricky because it's new stuff every day. Lots of vocabulary. What are you doing to remember the vocabulary? Are you making flashcards? Are you quizzing yourself? Are you talking to yourself out loud when you say, this is the tangent, and this is the chord, and this is the central angle, and this is the measure, and this is the length? Because the more that you talk to yourself, the more you're likely to remember the words. If you are doing nothing extra to process all of this information, our 90 minutes in class, even if you're super tight, are not enough. If you're paying attention to every single thing that I'm saying and you're doing everything I'm saying, it's not enough. Unless you're also doing the independent practice and the Delta math. So you have some practices here for you to work on, and you have a Delta math for you to finish. If you are behind on your geometry, I don't know what else I can say to beg and plead and encourage you. Come after school, come before school, take the time, because we're only halfway through the unit and there's so much more to go. So we want to make sure that you're processing this and that you're set up for success. Do me a favor, turn to your partner and tell them what your to-do list is in geometry. Turn and talk about it. Go.
Finish Delta math, do my homework, make a